Hi all. Section 5.6 is a pretty short section dealing with applications where we're looking at net change, displacement versus total distance traveled. So just as a way to introduce the concept, let's say I ask you to draw a graph representing the distance traveled if the rate is 75 miles per hour for a time of 2 hours. Well, you already know that distance equals rate times time. So if the rate is a constant rate, you can just multiply and say 75 times 2. But now, to show you how that's going to work within an integral process, you'd just say, well, for this simplistic scenario, we know that we have a constant velocity function. So that's the change in position with respect to time. So I'd say, well, that constant velocity function, think about what the area underneath it would represent. If the horizontal axis is represented by time, then if I wanted to find the area inside of that rectangle, which is the area under the curve, be again 75 times 2, which will give you your 150 miles traveled. So since integration gives area under a curve, not only in this scenario, but in all scenarios, even when I don't have a constant function, all I would have to do is say, I need to integrate from where the motion begins to where the motion ends to find the displacement over this period. So I would say from 0 to 2 hours of the velocity function 75 integrated with respect to t. That gives me 75t evaluated from 0 to 2, which of course is 75 times 2 minus the initial position, 75 times 0, gives me my displacement. I've traveled 150 miles over this region. Now, that makes the basic problem, the simplistic scenario where you have a constant function, more complicated, but it's going to make the other scenarios possible. So I can't simply just multiply by whatever the time is if my velocity function isn't a constant. What if the velocity function is a function in and of itself? Then you would have to do it this way. So now I can say, in general, we can say displacement is the integral from where the velocity is beginning to where it's ending of that velocity function with respect to time, and that's going to equal the displacement from the first time to the second time. Now, whenever we're thinking about displacement, it's important to remember that displacement can be negative. The reason I say, could displacement be negative? Sure. Well, think about this. If you had a positive velocity initially, followed by a time period where you had an extremely negative velocity for a longer amount of time, then you could say, well, the area between the x-axis and the curve is going to equal the total distance traveled. Well, the total distance traveled in this case, or I should say, it's going to equal the displacement over this period. And I can say the displacement over this period, there's more backwards movement than there is forwards movement. There's more area underneath the curve than there is above. So I can say, well, yeah, this would be a case where we have negative displacement. Now, on the other hand, if we talk about the total distance traveled, if I just wanted to know, well, how far to the right has he traveled in this period? How far backwards or to the left did he travel in this period? Then we would be looking for the total distance traveled, which is always an absolute value of whatever your velocity function is. So it would not allow the velocity function to turn negative in this region. You would just say, well, it's going to be up here as well. And you would just be finding the total distance traveled in that case. Now, to look at some problems that deal with this. Let's say, for example, I want to find the displacement over the time interval 1 to 6 of a helicopter whose vertical velocity at time t is v of t is equal to 0.02 t squared plus t meters per second. So you're given the derivative function, we know velocity. So to find the displacement, we can say, well, the displacement is going to be the integral of velocity from where the motion begins to where it ends, from 1 to 6. So we just integrate that function with respect to time. When we integrate it, we get 0.02 t cubed over 3 plus t squared over 2. We're evaluating that integral from 1 to 6. When I evaluated it at 6, I had 0.02 times 216 over 3 for 1.44. 6 evaluated into the second term gives me 36 over 2 for plus 18. So that's my top limit. We know that we always subtract from that the evaluation at the lower limit. Well, at the lower limit, I just get 0.02 over 3, which was the 0.0006 repeating, plus 1 evaluated into the second term just gives me 0.5. When I subtracted that out to 3 decimal places, I got 18.933. And remember, displacement in this case, I put feet there, but I should have put meters. So please keep in mind the units has to be the units of the original problem. So that should be meters there. Now for the next one here, and it is in feet, so I'll put the correct units for this one. I'm asking you to find the displacement and total distance traveled for a particle in its first 6 seconds of movement if the velocity function is 32 minus 2t to the second feet per second. And I'm asking you to draw a motion diagram for the particle. Okay, so displacement is never an issue. You can just say, well, the displacement's the integral from where from where the motion begins to where it ends. That's from 0 to 6 seconds of that velocity function with respect to time. So when we integrate, we get 32t minus 2/3 t cubed. And then we're evaluating that from 0 to 6. I know I don't even need to worry about the lower limit because this polynomial evaluated at 0 is just going to be a 0. The only answer I'll get is when I plug in the 6, and that gives me 6 times 32 for 192, minus 2/3 times 216, which is 144. We get 192 minus 144 for our total displacement of 48 feet. So that's telling me that the displacement or the change in position from 0 to 6 seconds, it's 48 feet to the right of where it started the movement at 0 seconds. Now that doesn't necessarily mean it traveled 48 feet. That's how far to the right it is at the end of this point of motion. But for part B, I want to find the total distance traveled. So when I'm doing that, I would just go ahead and think about when is this velocity function positive? So you'll see I said, well, the velocity function 32 minus 2t squared. If I try to find when that's greater than or equal to 0 here, this would factor really nicely. I could factor out a 2, and then it would be 16 minus t squares, which factors by difference of 2 squares to 4 minus t and 4 plus t. So now I graphed out the original function. I know that the original function, it's a negative quadratic. All negative quadratics start low and end low. It's going to have horizontal intercepts at -4 and +4. Now, we're only talking about time in this problem, so the only relevant x-intercept, or t-intercept, I should say, is at 4. So what I know is that the velocity is always positive until I get to 4, and then after that, the velocity is going to be negative. Thus, the absolute value of your velocity function, it doesn't have to do anything for the times between 0 and 4. So anytime t is a value between 0 and 4, it's going to give me a positive or a 0 when t is equal to 4. But then for any value after 4, like if you plugged a 5 into that, you get 32 minus 50. Well, you can't say that you're going -18 feet per second in this problem because we're trying to find the total distance traveled. So in that region, you would say, well, let's just take the negative of whatever the velocity is to ensure that the velocity is always positive so we can find the total distance traveled. So when t is greater than 4, we'll go in and say the absolute value is going to act as the negative of that function. Now, when I go in and try to find the total distance traveled, I have to break up the original problem from the integral from 0 to 6 and say from 0 to 4, the absolute value does nothing. So I just have 32 minus 2t squared in there with respect to t. And then from 4 to 6, it's the negative of that. Instead of putting the negative, I just flipped my limits of integration. Same thing as subtracting the integral from 4 to 6. Either way you do it, as long as you adjust for that sign one way or another by either putting the minus there and integrate from 4 to 6, or do like I've done here and switch your limits of integration. That is going to guarantee that I get a positive distance traveled for this last time period of between 4 and 6 seconds. Now, just as before, we integrate the function to get 32t minus 2/3 t cubed. We're evaluating that from 0 to 4. When I evaluated from 0 to 4, I found that it's traveled 256 over 3 feet in that time period. When I evaluated from 4 to 6 by switching the limit, since I knew it was going to give me a negative, I plugged the 4 in again. Of course, it gives me 256 over 3. When I plug the 6 in, it's going to give me a 48. And I always say upper limit of integration minus the lower limit of integration. 256 over 3 minus 48 is going to give me a positive value. Now, what I know is happening here is that, well, it's traveling this 256 over 3, so it's going approximately 85.3 feet to the right in the first 4 seconds. And then in the last 2 seconds, it's traveling 256 over 3 minus 48. It's traveling 37.3 feet backwards in that period. But now, because I have the absolute value of my velocity function and I'm getting only positive values from this is going to treat both of these distances as a positive value. So I can say, well, then my total answer here, if I say 256 over 3 times 2 minus 48, it's giving me 368 over 3. So I could have gotten that same answer by just adding these two values here, the distance to the right plus the distance to the left, and you would get your total distance traveled of 122.667 feet. Now, in the motion diagram that I did here, I just tried to show that in the first 4 seconds, it's traveling 256 over 3 feet to the right. In the final 2 seconds, it's traveling back to where the total displacement in this region is 48 units to the right, but that distance backwards was 37.3 repeating feet to get to that final answer of 48 for the displacement. That motion diagram really gives a good picture of what's going on in this problem, but the main thing in order to work the homework problems is to understand the distance between displacement and total distance traveled. The difference being the displacement, you just integrate from where the motion begins to where it ends. The displacement, it's the integral of the absolute value of the velocity function. So you have to consider when the velocity is going to be positive and when it's going to be negative and how that's going to impact your answer for the total distance traveled. Absolutely cool section. Go ahead and try the homework through there, and I'll be glad to help out wherever needed.